Hi, Chuck.
Hi, Murtaza. How are
How are
you?
you?
I'm great, thanks. How are you?
I'm good. I'm good. The traditional tradition at Ryerson is that we start 10 after.
Ah,
So we'll just probably give a few more minutes. We
okay,
have 35 participants already, and I
great.
think by within 5 minutes or so, we'll see others joining us. So this gives us a chat time to warm up a bit.
Oh, great. Did you
So
want me to test the screen sharing thing again just to be sure, or
yes,
I'm
so
sure it's
I'm
fine.
gonna remove the screen share that I have, and
Okay,
so that you can. So now you could you kindly share your screen so that goes on the mains.
certainly. Can you see it?
Absolutely, it's right there. Good.
Okay, great. You want me to leave it on there, or you want me to
So
take it
that would
back
be
down?
good. That would be
Oh, okay.
very
That way people
excellent.
will know
So
what we're here
great.
for. How was class? You had to go teach, didn't you?
Yes. So the students are now switching from the class to this.
Ah,
So I just did a sort of an expose of the margins command, but the R
ah,
version of it. But the
uh-huh.
example I use is from the Stata manual. So
Okay.
there's a margins manual that comes in, but 60 pages of margins, which is amazing. So my favorite is example 6 and 7. Um,
Yes.
so so I use that as a way to illustrate, and it was quite interesting because some students said, "Well, why?" So the example has gender in it, male
Mhm.
and
Yes.
female.
Yes.
So there's a dependent variable and outcome variable. So we are saying, what is the predicted value for the outcome for treating male as males and then treating males as females? And
Uh-huh.
then they're saying, well, why would we do that in the first place? I thought, well, that's what counterfactual is, right? Like if you
Right.
have a program, some people took part in the program, others didn't, and you want to
Yeah.
know what the outcome would have been had those who took the program not taken the program. So that example is very convenient to illustrate that. That's why I always
Yeah.
use the that particular data set from Stata
Right.
to
Uh-huh.
illustrate those examples. So far we have about 39 participants, and
Okay.
I'm going to stay true to Ryerson's commitment for another 2 more minutes, and then we can start there.
Okay. Would you prefer to take verbal questions during the talk, or would you rather wait till the end? Do you have a
I think
preference?
what I would say to attendees is that if they can, I will have the chat box open. I hope that I can see the
Okay.
chat if there is one. There should be.
There is, but I won't be able to see it during
Yes.
the
So
talk.
what I was hoping is that if I could see the questions, and then I can be the person putting those questions to you.
Oh, sure, that'd be fine.
So like I will be monitoring the chat. The only thing is I have to minimize the screen. I have a big screen.
I
My
just use my
student.
laptop, my very old laptop.
I have like the the traffic command and control center kind of an environment
Oh
here.
yeah. Yeah.
It looks more
Yeah.
impressive than the work being done here.
I didn't have I didn't own a any kind of computer until I went to work for StataCorp because I had worked in universities for so long.
Oh yes.
I always had them through the university, and I tried to avoid working at home as best I could, which didn't work out very well. But I finally, when I went to work for Stata, I had to buy a laptop. I have a Stata laptop as well, but it's old. It's probably almost 9 years old now.
Yeah. No, it's I always had two offices, one at home, and actually when I was there was a time when I had my office at McGill,
Uh huh.
my home office in Montreal, and because my family was in New York at that time, so I had a sort of a corner in our New York house as well,
Uh
where
huh.
I left a very old desktop just in case. Uh,
Yeah.
so at one point I was been shuffling with three laptops or three computers. So I think it's a good time to start. We
Okay.
have about 41 participants. The
Okay.
only thing is, could you kindly unshare the screen for just 1 second?
Certainly. There we
Okay.
go.
This allows me to see the chat button once again.
Okay.
And I'm going to bring the chat button here. And
Okay.
now I can so this is good. Let me do the introductions first. So folks, thank you for
Okay.
joining us today. Today we are delighted to welcome Dr. Chuck Huber from Stata Corp. And the seminar today that we are attending is the causal inference for complex observational data with Stata. I would not talk about anything about the conversation that you will hear from Chuck. But I would talk a little bit about him because I think think of Chuck as the brand ambassador for statistics. And the reason I say that is that if you have been stuck in your research in some question and you wanted to know how to solve it, and then you go on Google it, and when you Google it, you end up on a website, and that YouTube, and then there's a video. Chances are it's Chuck's video that will help you understand what you were trying to do, because his videos for the Stata YouTube channel are phenomenal, and they are have a global following in explaining, taking statistical methods, taking econometrics, and taking them and making them palatable for the uninitiated. Because when experts talk to experts, that's important, but not really as useful when this knowledge, this specialized knowledge, is translated and it's conveyed to people, to students, to learners, to practitioners all across the globe who may not have the good fortune of being trained by experts in the field. So for this reason, I think Chuck is the brand ambassador for statistics and data science. He works for Stata Corp. He's the director of their statistical outreach program. In his past life, he's been an academic, a professor. He continues to teach courses. I think the field of research that he has contributed to and continues to contribute is biostatistics. Would that be okay, Chuck? Biostatistics is your...
Yes, that's my training, and I still teach a class in biostatistics actually for Texas A&M. So I'm still an academic in a peripheral sort of way.
Very good. So he this is one other thing that I know. I came to statistics from an engineering background, trained as a civil engineer. And Chuck is a biostatistician. So I think statistics or data science is large enough to absorb all academic or professional disciplines and allow people to find their own way of seeking the truth through numbers. So today's discussion, we are very delighted to have you at the Ryerson University. This is, I think, your first time presenting here, and the Urban Analytics Institute is delighted to have you. And the way we will work is that I think we have an hour or so of a presentation followed with some question and answer time period. Chuck has generously agreed to stay as reasonably long as questions are there, for which we are very grateful. And then I think the way to work is that you have two options. You can type in the questions during the presentation, which will be in the chat section, and I will read them, and I will interrupt Chuck and say, Chuck, there's an interesting question that needs answering now rather than later. And at the same time, I would prefer that if everyone keeps their microphones muted and their cameras off, because we are also recording this. Chuck has also generously agreed to allow us to share this online, which we will put online later. So which means that if you keep your video cameras off, then you don't run the risk of inadvertently being part of our recording. So this is for me to let you know that this is being recorded, this meeting. So you will, if you don't want to be seen, make sure that your cameras stay off. At the end of the presentation, you're welcome to unmute yourself and have a conversation directly with Chuck and ask questions. During the presentation, please do not hold back your questions, just type them up and I will read them for you. So this way we don't have many people speaking over each other during the presentation. So with that, Chuck, it's over to you.
Well, thank you so much, Professor Hayner, and thank you for inviting me to be here today. My only regret is that I'm not there in Toronto. I love Toronto. I always think I've been there more times than I have, but that's because I used Toronto as a home base to visit other universities for a while. And so I would be in Toronto and then somewhere else for a while and back in Toronto and then somewhere else. And so it felt like home there for a while. But anyway, thank you again for having me. And I think I will go ahead and share my slides. Let me see, share my screen. And we'll get started. Okay, can you see the slides okay?
Absolutely.
Okay, perfect. And I'm going to disable my video just to, so I'm not taking up too much bandwidth here. Okay, so today we're going to be talking about causal inference for complex observational data, and of course using Stata. If you'd like to download the materials, you can grab all of the slides and the data sets and the do files at this tiny URL. If you're interested in doing this sort of work, one of the little sort of gems that's available in this at this website is also the do file that I use to create the simulated data set. And I'm not boasting about that on my part. The guy who created the ERMS command, Charles Lindsay, spent a lot of time with me teaching me how to do how to use ERMS and about the underlying material. And he also showed me how to simulate data to try this out. And so that there's a do file included in this folder that will allow you to create simulated data sets under the assumptions that we'll be talking about today, the assumptions that or the complications that we'll be talking about. And that took me about a day to write, even with coaching from Charles Lindsay, the guy who wrote these commands. So check that out if you're interested in doing simulation studies or things like that with ERMS. Okay, so I've already used the word ERMS a couple of times. What does that mean, ERMS? ERMS stands for Extended Regression Models, and so that's essentially what I'm going to be talking about today. Uh, uh, we're going to start off with a description of the data set, which is a simulated data set. And then I want to go through and talk about three common features of observational data that we often encounter. First up is unobserved confounding and endogeneity. Second is non-random treatment assignment. And third is data that are what's called missing not at random, or MNAR, which can lead to a phenomenon called selection bias. And then we'll wrap up by talking about treatment effects towards the end. So this is our research question. Fictional State University, FSU, this is entirely simulated data. It's an entirely fake story, so don't believe any of it. It's just an example. So Fictional State University has developed a new study skills program with the goal of improving the students' grade point averages. So ideally, this should be a pretty simple study, right? We have a binary treatment. You either take the study skills program or you don't take the study skills program. And the dependent variable is a continuous variable, grade point average. And so in theory, this should be a pretty simple study, right? We could have a calculate a t-test and be done with it. But as we're going to see, there are a lot of complications along the way that are going to make this not as simple as just a t-test. So let's take a look at our data set first. So this data set is called GPA. And again, it is simulated, so don't believe anything in here. So the variables that are in this data set include, by the way, there are 1,000 observations. So this is a good sized data set. The first variable here is ID. That's the student's identification number. And then I have a variable called GPA, which is the student's final college GPA. Then I also have a variable called HSGPA, which is the student's high school grade point average. And we collect that on their way into college. Then I have a variable called program, which is an indicator variable for whether or not the student participated in our study skills program. Then I have a variable called graduate, which is an indicator for whether or not the student graduated from college. Then I have a variable called income, which is the parent's income measured in hundreds of thousands of dollars to keep the numbers very small. And then I have a variable called HS underscore comp, which is a measure of high school competitiveness. It's a continuous measure. I made this one up just out of thin air, but my understanding is that, at least in the United States, the College Board has developed an official measure of high school competitiveness. That is not what this variable is. I just made it up. It's a continuous variable, and I needed it for my example. And then I have a variable called roommate, which is an indicator for whether or not the student's roommate is also a student. And we'll come back to why that's important later. And then at the last variable here is called scholarship. And that's a needs-based, it's an indicator variable for whether or not the student received a needs-based scholarship. Has nothing to do with, it's not a merit-based scholarship for high GPA or things like that. It's strictly a financial aid. Although in Canada, this that variable may not make sense in Canada. The United States has a strange way of funding college. But anyway, that's what scholarship is for. So the first thing I do with any data set is I like to summarize the data set. And I'm not really interested in the means and standard deviations. What I'm interested in is, first off, is the OBS column here, because I want to know if I have a lot of missing data. So if I scan down the OBS column of the list of variables here, all of the variables have 1,000 observations except for GPA, college GPA. So I only observed 792 observations for GPA, which is a shame because recall GPA is kind of our primary endpoint. We're interested in the effect of the study skills program on the student's college GPA. And so we're missing a sizable proportion of data for our primary endpoint GPA. The other columns I like to look at are the min and the max column. I'm looking for unusual values, things that don't make any sense. People that weigh negative 30 kilograms or people that are 730 years old, things that just don't make sense. So if I scan down the min column here, things like GPA, minimum GPA of 0.339 seems reasonable. The rest of these numbers all look reasonable because it is, of course, simulated data. But it is a nice way to get to know your data. So the first thing I'm concerned about here is this missing data, though. So I'm missing some data for GPA. So if I tabulate the variable graduate, remember that graduate is an indicator for whether or not the student graduated from college. And we only record the student's final GPA if they graduate from college. It's their final college GPA. So if the student never graduated from college, we never actually observe their final college GPA. So we're missing 208 values for college GPA. 208 students of these 1,000 never actually graduated from college. And that's actually pretty typical. Sometimes the number is a little lower, sometimes higher, but it's not unusual at all for some students to begin college and not finish. So that explains why we're missing some data for GPA. And we'll come back to how we're going to deal with that later on. I'm just exploring the data at this point. Now, another thing that I like to do, and I have colleagues who make fun of me for this, but I do it anyway because it's saved me on a lot of occasions, is I like to look at a histogram of my primary dependent variable. And I've overlaid a normal distribution on it, and I realize the variable does not have to be normally distributed. The errors, it's nice if they're normally distributed, but linear regression and linear models are robust to departures. But what it does allow me to do is, first off, I get to see the distribution of the data. If I have a bimodal distribution, for example, that could cause serious problems with my estimation. If I have wildly skewed data, that might cause some problems. But anyway, it takes 2 seconds to do this, and it saved me on many occasions identifying strange values and things like that. So here, our primary endpoint, final college grade point average, looks very, very neat and normal looking. It's also your first clue that these are fake data because real data are never that clean and normal looking. Okay, so the next thing I want to look at is something called a scatter plot matrix. And often people use correlations. I see this a lot with investigators. They'll get some data and create a correlation matrix and then look for high correlations in their correlation matrix. And that's fine as long as you remember that linear regression or correlation only measures the degree of linear relationship between two variables. And often we have U-shaped or hump-shaped or S-shaped scatter plots. And so I like to use scatter plots to explore relationships between continuous variables because this will allow me to identify other kinds of relationships other than linear. So I have 3 variables in this scatter plot matrix. In the top left, I have final college grade point average. The middle variable is high school grade point average. And then the bottom right variable is parents' income. So if I look at the scatter plots, one of the first things that jumps out to me is that final college grade point average and high school grade point average are highly correlated. And that's really shouldn't be surprising, right? Because if you did well in high school, you're probably going to do well in college. So no surprise there, but it is a feature of our data that we need to keep in mind when we're building our model. High school GPA and college GPA are highly correlated. If we look at the graphs for parents' income and high school GPA, there also seems to be a bit of a relationship between parents' income and high school GPA, and to a lesser extent, parents' income and college GPA. But there does appear to be a slightly positive slope to that cloud of points there. So again, I'm not trying to really draw inferences here. I'm just looking for patterns in my data before I start building a model. The other thing, and I know a lot of people hate pie charts, but I sometimes use them for things like this because it's just quick and easy. So you might, if no one told you, you might assume that 50% of the students took the study skills program and 50% did not. Because if we were going to design an experiment, of course, we would allocate 50% to one group and 50% to the other. But in this case, in this data set, 70% of the students did not take the study skills program and only 30% did take the study skills program. So we don't have balanced groups of participants and non-participants. So again, it's just a feature of our data as we're going through and getting to know it. Now let's start looking at some relationships here. On the horizontal, I have two box plots, and the horizontal axis here is the final college grade point average, final GPA. And the top box is for students who did not take my study skills program. And the bottom box is for students who did take my study skills program. And you may be wondering, wait, is there a mistake here? Is it mislabeled? Sadly, it's not. So the students, what this graph is showing us is that students who did not take the study skills program had generally higher final college GPAs than students who did take my study skills program. Well, that's unfortunate because the goal of the study skills program was to improve students' GPAs. And here it would suggest that we may have harmed them, possibly. We're not really sure, but it's lower in that the GPAs are lower in the group that took the study skills program. So that seems a bit counterintuitive. Something must have gone wrong here. But again, it's just a feature of the data. But I can fit a linear regression model for GPA. So I've typed regress in Stata. I've typed regress. GPA is my dependent variable. And I've placed an I dot in front of program to accentuate the fact that program is an indicator variable. So the I dot tells Stata that program is a categorical variable. Anyway, so if I look at the coefficients, sure enough, the study skills program has a negative coefficient. So it suggests that students who participated in our study skills program had lower college GPAs. And the p-value is even 0.017. So that suggests this isn't just a trivial finding here. So let's take a look at high school GPA. We also have the students' high school grade point averages in our data set. So the horizontal axis now is high school grade point average. And then I still have the two box plots. So the box plot on the top is for students who did not take my study skills program. And again, the box on the bottom is for students who did. Now, what makes this graph interesting is that this suggests that students who took my study skills program had lower high school GPAs coming into college. And if we think about that, lower than the students who did not take my study skills program. And what's interesting about this is that obviously, if we think about the temporal order of these events, we collected the students' high school GPA before they took the study skills program. So there's no way that our study skills program could have harmed or caused these students to have lower high school GPAs because high school GPA was collected first, and then they took the study skills program later while they were in college. So what does that mean? Well, we're going to have to come back to that and explore that. But if we fit a linear regression model, again for GPA, and we include program as an indicator variable in our model, but if we also include high school GPA, we're adjusting now for high school GPA, notice that the coefficient has flipped signs. So now this is when we adjust for high school GPA, our study skills program shows a positive effect for for the students' college GPA. So, okay, let's look at some other, we're just getting to know the data. We're not really fitting major serious models yet. We're just sort of exploring our data set. Now the horizontal axis, let's look at the proportion or percent of the students graduating. For this, about 83% of the students who did not take my study skills program graduated. Of the students who did take my study skills program, about 69% graduated. So again, lower graduation rate for students who took my study skills program. And finally, if I look at high school GPA by graduation status, sure enough, the students, the top box is for students who did not graduate, the bottom box is for students who did graduate, and not surprisingly, the students who graduated tended to have higher incoming high school GPAs. So what does all of this mean? We've kind of glanced through our data, and there are some intuitive and not so intuitive patterns in our data set. But the question that we really want to answer here is, what was the effect? Is there a causal effect of the study program on the students' college GPAs? And so that's where we're headed with this talk. So let's talk about unobserved confounding and endogeneity. That's the first complication we're going to talk about. And to do that, I want to rewind all the way back to the very beginnings of linear regression. And let's think about first principles. What do we really mean when we're fitting a linear regression model? So let's say that y, and let's do this in the abstract. Let's just talk about y as some generic dependent variable. So when we fit a regression model, what we're essentially saying is that y is equal to all of the possible factors that could influence y, everything you can imagine. And we're going to divide those factors into two groups. The first group are the observed factors. Those are the things that are in our data set, things that we can measure, and things that we're going to include in our model, covariates, X's, and things like that. But there's another group of variables that are the unobserved factors. And the unobserved factors get lumped together into the sort of statistical garbage can of the error terms or the residuals. And so anything we don't observe gets lumped together in that error term. Okay. So again, we have all of the factors that could influence y. We divide them into observed factors and unobserved factors. And then we're going to set up a regression model that looks something like this at the bottom. So next, let's talk about some just definitions. So if I'm fitting a regression model, there's a phenomenon called endogeneity that can sometimes occur. And you guys are probably familiar with this term being in a management school. But just as a quick definition, Jeff Wooldridge defines endogeneity as an explanatory variable in a multiple regression model that is correlated with the error term. This comes right out of Wooldridge's Intro to Econometrics book. What does that mean exactly? What that says is that we have a covariate in our model. Let's say that covariate Z here, or Z is correlated with the error term in the model. Well, that's a strange thing. Usually we assume that that's not the case, but that's in fact the definition of endogeneity. A covariate is correlated with the error term. Well, how can that happen? Well, one cause of endogeneity is a phenomenon called omitted variable bias, and you're probably familiar with this, but just as a quick review, omitted variable bias means that we have a couple of variables in our data set and our covariates in our model that may be correlated. And this is actually quite common. It's called multicollinearity. So let's say that the covariates X and Z are correlated. And we know this. We know this from prior research or whatever, that X and Z are correlated. But if we omit Z from the model, well, Z didn't disappear. Z actually moves from being an observed factor to being an unobserved factor, becomes part of the unobserved part of the model. And so if we omit Z from the model, again, Z becomes part of the error term or the residuals. So now rather than having error, we have error star for our model, for this middle model right here. And error star actually contains Z along with the rest of the error term. So if X and Z are correlated and we omit Z, then X and the error term must be correlated. They must be, because Z is now contained in the error term, okay? So that's one way. Omitted variable bias is one way that you can end up with this phenomenon of endogeneity. Now, why do we care about this? Well, as the name suggests, omitted variable bias. Well, the bias that can occur is in the remaining parameters in the model. So if I omit this, if I omit Z and I have correlation between X and the error term, that can actually bias beta 0 and beta 1, our estimates of beta 0 and beta 1. And this is a well-known phenomenon, and so we need to check for this and possibly account for it. Now, another way of thinking about this is called confounding. It's a similar idea, but just so we're aware of the term, Judea Pearl in his book on causality defines a confounder as X and Y are confounded when there is a third variable Z that influences both X and Y. So in this case, X and Z are, X could influence Z and Z could influence X. And we also believe that Z could influence Y. Otherwise, we wouldn't have it in the model. And so that would suggest that Z is a confounder in our model. But again, what happens if Z is omitted from the model? We have the same omitted variable bias kind of problem. But epidemiologists and many people in the health sciences refer to this as unobserved confounding. So whether you want to call this omitted variable bias or unobserved confounding, it's the same idea. We have a variable Z that's been omitted from the model, but it's correlated with another covariate in the model, and this induces correlation between a covariate and the error term. All roads lead back to this problem of endogeneity. So what does this have to do with our particular question today? So let's think about GPA in these new terms. So let's say that GPA, college GPA, is equal to all of the possible factors that could influence GPA. And we're going to divide those factors into two groups. Again, the observed factors and the unobserved factors. So the observed factors in our model might be things like high school GPA, SAT scores, standardized test scores, parents' income, sex, and things like that. And I was trained as a biostatistician, and we didn't really talk about unobserved confounding as much, and we certainly didn't talk about endogeneity much. And so this is an area where I think economists have really led the way in teaching us to think about what are the unobserved factors that are bundled up in the error terms. So let's think about the unobserved factors, things we didn't observe that could influence college GPA. Well, those may be things like overall ability, maybe motivation, sleep, although we can kind of measure sleep now with these fancy watches and things like that. But things like support, emotional support from friends and family, those are all things that are difficult to measure. We certainly believe they influence your college GPA, but we don't really observe them directly. And so they all get bundled up in the error term as unobserved factors. But let's think about one of these for a moment. Let's say that ability, it's one of those things that's hard to define, but we all sort of recognize it when we meet new people or work with people and think, wow, that person seems to be a person of high ability or lower ability, at least in certain areas. And so we could probably stipulate that there is such a thing called ability, even though it's difficult to measure. So let's say that ability exists, and we believe that ability, overall ability, influences college GPA, but we also believe that ability influences your high school GPA. Well, since we don't observe ability, that means that we're going to have this problem with unobserved confounding. Okay, because we didn't observe ability, it's bundled up in the error term, and ability is associated with high school GPA or correlated. All right. So this means we could have a problem with endogeneity. So how are we going to deal with this? Well, a common way in econometrics, and you're probably familiar with this technique, is let's say that we want to fit the model where college GPA is the dependent variable, and I'm going to include the covariates income and high school GPA, but I believe ability is an unobserved confounder. What I'm going to do is I'm going to take high school GPA and I'm going to split it off into its own auxiliary model. So high school GPA is a covariate in the main model, but it's going to become a dependent variable in an auxiliary model. And in the auxiliary model, I want to include a covariate that has a couple of special properties. First, I need a variable that's associated with high school GPA. But I need that same covariate to not be associated with ability. So I need those two properties. And so in this case, the variable, the covariate that I'm going to use in my auxiliary model is high school competitiveness. So here's the argument. High school competitiveness probably influences your high school GPA. But high school competitiveness is a feature of the high school, not the student. And so high school competitiveness shouldn't be related to a student's ability, unless they're placed in certain schools for certain reasons. But let's just pretend, for the sake of this example, that high school competitiveness is not related to an individual student's ability, but high school competitiveness does influence the student's high school GPA. So we're going to split off high school GPA like this into its own auxiliary model. And then what we're going to do is we're going to take the expected value of high school GPA from the auxiliary model. And the expected value is the part shown in green here. And we're going to substitute in the expected value of high school GPA back in the main model. And by doing that, we've broken this link between the expected value and ability. We've broken that correlation, so that should remove any problems of endogeneity. And so what that suggests, though, is that if we have these two models, the error terms in both models have to have ability in them. And so because of that, the error terms are going to be correlated. Okay, so the error term for the auxiliary model and the error term for the main model, those errors are going to be correlated. All right. So that may seem a little odd. So often I talk to groups who are familiar with something called structural equation modeling, and I don't know if any of you are or not. Very quickly, what structural equation modeling is a technique for looking at the interrelationships among a collection of variables. And so rather than having a single left-hand side variable, we can have multiple sort of dependent variables. And we can also have things called latent variables. So let's just walk through this thing at the bottom here. Things that have corners, box-looking things, those are observed variables in our model. So I have high school GPA as an observed variable in my data set. GPA is an observed variable in my data set. Income is an observed variable. And then I've drawn my error term here with a circle. So arrows, excuse me, the circles are, excuse me, the error terms are drawn with circles. And I've drawn something called a latent variable with an oval. Latent variables in structural equation models represent variables that we believe exist, but we can't measure them directly. And so I've drawn ability here with an oval. Now the arrows that go between the different components here, those are called paths. And what we're going to do is estimate the coefficients for each of these paths, or the relative effect of one variable on another variable. And so, for instance, there's an arrow that leads from high school GPA to GPA. So we're going to estimate the effect of high school GPA on college GPA. Same thing with income. We're also interested in the effect of the latent variable ability, as well as the unobserved factors that are bundled up in E. So what I've done is I've drawn a path diagram, a structural equation modeling path diagram here at the bottom, to represent the equation above right here. And what I want to do then is I want to expand my structural equation model, or my path diagram, so that it takes into account both the auxiliary equation as well as the primary equation. So notice what I have now is that high school GPA is a predictor of GPA, but high school GPA is also a dependent variable, or in structural equation modeling terms, it's called, in jargon, it's called an endogenous covariate. And I believe that high school competitiveness influences high school GPA influences college GPA, and so forth. Notice that I've also drawn the two error terms separately. So I have epsilon 1, which is the error term for the primary model. Epsilon 2 is the error term for the high school GPA model. And then I've drawn ability as a latent variable here. It's, again, something that I believe exists, but I don't observe directly. So rather than try and estimate ability in these path coefficients, what I'm actually going to do is simply allow for I'm going to quantify that latent variable by simply allowing the error terms to be correlated. And that's how I can quantify the whether or not this this latent variable ability exists and what is its influence. Okay, so that's one way that I can account for endogeneity, or test for it. If the correlation is not equal to 0, that suggests that we do have this problem of endogeneity. Now, if you're not familiar, or if the latent variable thing seems a bit too abstract, let's draw this again and think of it a little bit more concretely. I have the exact same path diagram at the bottom, but rather than using a latent variable here in the middle, I've simply drawn the error terms and included ability in both of the error terms for each of the two models. And so if we think about the circles as the errors, we can think about the overlap in those circles as the covariance. If we think about the circles as the variance of epsilon 2 and the variance of epsilon 1, the overlap between them is the covariance, or correlation, represented by this overlapping notion of ability. So again, if the correlation is 0, that suggests there's no overlap in the errors, in which case we don't have this problem of endogeneity, and we can just go back and use our regular old regression model. But if we do have this problem of endogeneity, first off, the non-zero correlation suggests that we do have the problem. But then by fitting the model in a fashion like this that allows for correlation of the error terms, that also fixes the problem. It removes the bias, so to speak, from the omitted variable bias. So again, the model that we're going to be fitting in an analogous structural equation model is essentially this model right here, and I'm going to allow for correlation of the error terms. So I've gone this far down the structural equation modeling road. Let's go ahead and do this. So I've drawn this in Stata's structural equation modeling builder. And if I fit the model, I can see here that the correlation between the error terms is 0.88. 0.88 is a pretty high correlation. And so that suggests that we do have a problem with endogeneity. But the good news is, by fitting the model in this fashion, we've also fixed the problem. We've identified the problem, but by allowing and estimating the correlation in the model, we've also hopefully removed any bias in the parameter estimates in the model. Okay. So the way to diagnose it is also the way to fix the problem. So what does this have to do with extended regression models? So in Stata 15, we introduced the eRegress command for extended regression models. And I'm going to show you the linear version. There are others, and I'll talk about those later, but I'm just going to show you the linear version for now. So the command is eRegress, which stands for extended regression models. And then the syntax is very similar to the regress command. The dependent variable is GPA. And then I'm also going to include income in my primary model. So income is a continuous covariate. And then these 3 slashes at the end of the row here, that tells Stata that this command is going to wrap around onto the next line. It continues on the next line. And then I'm going to use the endogenous option to specify my auxiliary equation. So here I'm going to have a dependent variable, HSGPA, high school GPA, and I'm going to use high school competitiveness and parents' income as predictors of high school GPA, okay? Now, what's implied here is that HSGPA is also a covariate in the primary model. Now, Stata won't complain if you type eRegress GPA income HSGPA and then type endogenous HSGPA and so forth. Stata doesn't care. It'll accept it either way. But just be aware that if you don't include HSGPA in your primary model, Stata is going to do that for you anyway. So you'll see in the output that HSGPA is also one of the predictors of college GPA. So we have our primary model, and then we have our auxiliary model. And when we actually fit the model, at the top you can see the command is eRegress GPA and so forth, just how we set it up before. And our output, I have 2 sets of coefficients. The top set of coefficients here, see where it says GPA in the top left of this first section. That's the part of the model where GPA is the dependent variable, the primary model. And I have 3 predictors, or 3 coefficients. The underscore const, that's the intercept or the beta 0. And then I have the effect of high school GPA and then parents' income. So I see those coefficients. And then below that, I see where it says high school HSGPA. This is the auxiliary model where a high school GPA is the dependent variable. And again, I see 3 coefficients. This time I have underscore cons, which is a separate intercept. And then I have parents' income as well as high school competitiveness. So I have essentially 2 models, the main model and then the auxiliary model. And then below that, I see estimates of the variance of the error terms for each model. So the first is the variance of the error term for the GPA model. So that's what this E.GPA refers to. So E.GPA is the errors from the GPA model. So I have an estimate of the variance of those error terms. And then below that, I have an estimate of the errors for the high school GPA model, the auxiliary model. So I get estimates of the variance of the error terms for each of those. And then at the very bottom here, I see the correlation between those error terms. So on the next slide, I'm going to zoom in on this bottom part of the model. So here we've estimated that the correlation between the error terms is 0.75. And the p-value is 0.000 and probably goes off to some more zeros. And what this suggests is that we do have a problem with endogeneity because our error terms are correlated. But the good news is by fitting the model with the eRegress command like this, that should have removed any bias that we had before. So we should be able to trust these coefficients. So again, by identifying the problem, we've also solved the problem. So here what I've done, I don't know if you've noticed at the bottom of each of the models, I've typed estimate store and then given each of these models a name. And I've been doing that along the way without telling you, but what you can do is type estimate store after you fit a model, give it a name, and Stata will store all of the parameter estimates and things like that in memory temporarily. And then what I can do is type estimates table and tell it the names of those models, and it will show me the coefficients and other things if I want for each of these models. So the rows here, I have the coefficient program or the covariate program. I have HSGPA, income, and underscore cons. And then the 3 columns here represent the 3 models that I've fit so far. Univar is that very simple, naive model that I fit early on where I just included program in a regression model. And recall that the coefficient for program was negative. The second column here, HSGPA, that's the Univar model where I adjusted for high school GPA. And remember that the coefficient for program flipped and was positive. And then the third model I fit here is this, I've called it ENDOGE, which is the model that I just fit that takes into account the endogeneity of high school GPA. And so I don't want to spend a lot of time on the coefficients yet. I'm going to come back and fill in this table as we go, and then we'll compare these coefficients when we finish. Okay. So that's unobserved confounding and endogeneity. Do we want to pause here and take any quick questions on observed confounding and endogeneity before we move on?
I have a question.
Okay, fire away.
Yeah, well, it sounds like the E regress is used to handle the endogeneity problem. How does that different from the old command ivreg or ivreg2? And then the results, how's the result look like?
Excellent question. So up to this point, eRegress is simply doing what ivreg does. Now, this is the equivalent of if you were to use ivreg with the maximum likelihood option. So you can also do two-stage least squares with ivreg, and you cannot do two-stage least squares with eRegress. eRegress uses maximum likelihood. But other than that, up to this point, this is essentially ivreg. You're exactly right.
Okay, great.
But we're going to add some cool things to it, which makes it a little different.
Look forward to that.
Good question. Any other questions? Okay, so let's talk about non-random treatment assignment. So in a perfect world, the students would come in and we would maybe toss a coin. And if the coin lands, say, head side up, we'll say, okay, you're in the study skills group. And another student comes in, we toss the coin lands head side up, and they go to the study skills group also. Next student gets tails, so they go to the no study skills program. You get the idea. We've randomly assigned the students to the no study skills group and the study skills group. And by randomly assigning them to the two groups, hopefully we have randomly distributed all of the potential confounders, observed confounders, unobserved confounders. Any differences in the two groups should be washed out so that when we finish our study, if there's a difference in the average GPA in the two groups, the only reasonable explanation is the effect of the study skills program. Because ideally we've randomly distributed all the other confounders by random assignment. But that's not what we have here. What happened here is the students came in and we asked them, hey, do you want to be in the study skills program? Whoops, I didn't go to the next slide. And why is it not going? Here we go. So what we did was the students came in and we asked them, hey, do you want to be in our study skills group? And the first one says, sure, why not? I'll try it. Their friend comes in behind them and they say, well, sure, they went, I'll go too. Next person comes in and they're like, I did okay in high school. I don't think I'm going to take your study skills program. No, thank you. And so you get the idea. The students come in and they choose which program, whether they take the program or whether they do not. Well, this screws things up greatly because when we finish our study, we can't really say that any difference in final college GPA is due solely to the study skills program. It could actually be due to things that influence the choice to participate in the study skills program or not. And so we don't really know that. That's kind of a big question mark left hanging over our entire study. And it's again because we did not randomly assign them to the group. We allowed them to choose which group they belong to. So what are we going to do about this? Well, one way we can handle this is to actually create a model. So we can model the choice to participate in the study skills program or not. And so that's what we're going to do. We're going to build a model where the dependent variable is the choice to participate in the study skills program. And we're going to use a Probit model for this. I'll explain more why later, but we're going to use a Probit model. And again, there are going to be observed factors that influence the choice to participate in the program, but there will also be unobserved factors that influence the choice to participate in the program. The other issue that we're going to have to deal with is that at some point we're going to want to include program participation in our primary model, right? To see whether or not program participation influences college GPA. And so we're going to have to deal with that at some point as well. Well, when we do that, when we include program participation in the primary model, we've already stipulated that we think ability influences a person's college GPA. And we might also believe that a person's ability influences their choice to participate in the study skills program. And if that's the case, then again, program is an endogenous covariate. It may be correlate, program participation may be correlated with the error term because ability may influence the choice to participate in the program. If you did really well in high school, for example, or you just have higher scores or whatever, people of higher ability might decline to participate in the program because they don't feel like they need it. Okay. So how are we going to deal with this? Don't take this slide too literally. This is a mathematical analogy to what I did with high school GPA, but it's not literally exactly the same thing. But by analogy, what we're going to do is we're again going to take program, our endogenous covariate, and we're going to split it off into an auxiliary model where program is the dependent variable. But this time program, again, we're going to use a probit model. And again, I'm going to use a variable that has those two special properties. I need a variable that I believe influences the dependent variable in the auxiliary model, but is not associated with the unobserved confounder ability. So this time I'm going to use the variable scholarship. So this is a needs-based scholarship, has nothing to do with merit. So if that's true, what I could argue is that if you have more scholarship money, needs-based scholarship money, you don't have to spend as much time working. So you're not making coffee down at Starbucks, you're spending more time studying, or you have more time to study, but more specifically, you have more time to participate in the study skills program. So having more scholarship money might influence, or having scholarship money might influence your decision to participate in the study skills program. But since it's a needs-based scholarship, it shouldn't have anything to do with a student's individual ability. And so scholarship should work nicely as a covariate here. So again, this is by analogy, not literally. We're going to substitute the expected value of program participation in the primary model. And again, that breaks this correlation between ability and program participation. So here I've drawn this again as a structural equation model just because I like the visual. And again, I like structural equation models, and I do this talk often for people in behavioral science departments who think in terms of structural equation models. So notice again here, GPA, college GPA is the primary dependent variable. That's right smack in the middle. And I believe still that high school competitiveness influences high school GPA influences college GPA. I believe scholarship, needs-based scholarship influences program participation, and program participation influences college GPA. Each of these models has an error, and those error terms are correlated. And so that's it is a structural equation model that represents the model that we'll be fitting. So again, I'm going to use the eregress command, and I still have my primary model here where GPA is the dependent variable and income is my covariate. I'm still going to include the endogenous option here for high school GPA, but I'm also going to include the option entreat. And inside the entreat option, I'm going to include another auxiliary model, this time where the program is the dependent variable, and I'm going to include income, parents' income, and needs-based scholarship as predictors of program participation. Just ignore the no interact thing. I needed that to keep this really, really simple. Just kind of ignore it. Now, why did I use the entreat option instead of the endogenous option? Well, a couple of things. One, program is a binary dependent variable, and so I could use the endogenous option and then type comma, use the option and tell it that this is a binary variable and use a probit model. That would work. But entreat is a special option. What entreat does is it automatically tells Stata that program is a binary dependent variable. And it also tells Stata that the program is the treatment variable. That's the thing I'm interested in. I'm interested in the causal effect of program on the dependent variable GPA. And so by using the entreat option, it treats I can specify another auxiliary model, but that tells Stata that program is that's the treatment variable. And that will allow me to do some things in post-estimation. And we'll look at those later on. So I'm using the entreat option. And when I do this, now if I look at my output for my eregress command, I have 3 sets of covariates. Again, the top set of coefficients is for the GPA, the primary model where GPA is the dependent variable. And notice I have income and high school GPA, program participation, and the constant, the intercept. I get parameter estimates for all of those covariates in the model. And then I have another auxiliary model where program is the dependent variable, and I have the covariates _const, scholarship, and income. Now, keep in mind that these coefficients are for a probit model, and so you can't interpret them the same way you would interpret the results of a linear regression model. These are probit coefficients. And then the third set of coefficients, where high school GPA is the dependent variable, that's for our HSGPA auxiliary model. And again, I get coefficients for each of those variables. Now at the bottom, I again get estimates of the variance for each of the models, variance of the error terms for each of the models, as well as correlations. So I'm going to zoom in on this bottom part of the output. So notice that I get an estimate of the variance again for the error terms for the GPA model, that's the primary model, and I get estimates of the variance of the error terms for the HS high school GPA model, one of the auxiliary models. But I don't see a variance of the error terms for the program model, the auxiliary model where program is the dependent variable. So why is that? That's a popular question that we get in tech support. The reason we don't get a variance for those error terms is that it's constrained to be 1. If you're familiar with probit regression, you may recall that the error terms, the variance of the error terms is constrained to be 1. And for whatever reason, if you do this with structural equation models, it'll actually put it there and show you a 1 and then in parentheses tell you it was constrained. I'm not sure why we don't do that with eRegress, but just know that there is an imaginary third row here where the variance of the error term for the program model is 1, but it's constrained to be 1. But what I can do is I can estimate the correlation between the error terms from the program model and the primary model, the GPA model. So I'm estimating the correlation between those error terms, and that correlation is 0.45, and the p-value is 0.000. So that's kind of on the fence, right? I mean, 0.45 it's not a low correlation, but it's not exactly a high correlation either. So it suggests that we might have a problem with endogeneity, but it's probably not a huge problem. But for our purposes, we're going to go ahead and treat this as a non-trivial or an important correlation and leave it in the model, okay? Now, the nice thing is if I look at my estimates I typed estimates table here, and I'm looking at a table of the coefficients for each of the 4 models that I've fit. Now I've included program in the final model here on the right, in the far right-hand column where it says entreat. And the coefficient for the program is 0.3. So what that suggests is that for now I'm going to use I'm going to call it an association. Our program participation is associated with about a 0.3 higher college GPA. Well, that's it. It's participation in the program possibly leads to a 0.3 increase in students' college GPAs, but we'll come back and talk about that after we fit one more model here. So any questions about non-random treatment assignment and how we're dealing with it? Okay, well, next up, let's talk about data that are missing not at random, or MNAR.
I think we lost audio for...
Oh, can you hear me okay?
I think at least I lost audio. I don't know about the others, but I lost audio for maybe 20 seconds.
Oh, I'm sorry. Can you hear me now okay?
Clearly.
Yep.
Okay. So let me just back up then, since we may have missed some parts here. So next up, well, I had asked if anybody had any questions about non-random treatment assignment. Did I miss anything? Okay.
I heard that part.
Okay, great. So next up, we're going to talk about data that are missing not at random, which is often abbreviated MNAR, and the phenomenon that can occur called selection bias. So in a perfect study, the students would start as freshmen, and they would go along and they would take their classes, and we would observe them, and by the end they would all graduate, and we would have complete data and GPAs measured on everyone. So we would have no missing data, and that would be the ideal. But we know that's not the case, because we know that we had 208 students who did not graduate. So the question then becomes, why did they not graduate? Why are we missing this data? Whoops. So let's talk about some different mechanisms by which the data could have become missing. So first up is missing completely at random. So let's say the students are going along taking their classes, but for some of these students, something completely random happens. So for example, this student won the lottery. And oddly enough, a couple of years ago when I was creating this talk, a student in Florida, a college student in Florida, actually won like $500 million in the lottery. Well, if this student won $500 million, they're probably not going to show up for class and they're probably never going to graduate. They're going to go buy an island or something. Who knows? But they didn't graduate, and so we don't observe their final college GPA. Well, the good news for our purposes is that, well, let's bad news first. The bad news is we lost a bit of sample size, right? Because our sample size is not as large as it was. So we're going to lose a little statistical power. But the good news is because this is completely random, it shouldn't really bias the GPAs in our data set one way or the other. Shouldn't bias it up, shouldn't bias the GPAs down because it's completely random. So all we've done is lost a little bit of statistical power. So not the end of the world. That's missing completely at random. Whoops, here we go. Now let's talk about missing at random. So let's say the students are going along, and for some of them, something happens, like this student's mother lost her job and they can't afford to make their tuition payments. Well, recall in the data set that parents' income is associated with final college GPA. So there might be some information about college GPA that we could extract from the parents' income. I know that's kind of a stretch, but just roll with the example. So let's say that there's information in parents' income about the student's college GPA. What that would allow us to do is something called multiple imputation or full information maximum likelihood, or one of those sorts of techniques where we can use that information in parents' income or maybe other covariates to fill in some of the missing information about college GPA. So that's missing at random. We're still going to lose a little bit of statistical power, but we might be able to recover a little bit of it, again, using multiple imputation or full information maximum likelihood. Missing at random. But here's the really scary one for our purposes. It's called missing not at random. So the students are going along, and for some students, they just quit. This student just says, this is just too hard. I give up. Their GPA is already low. Maybe they're about to be kicked out. They're on academic probation. And so the student says, you know what, that's it. I'm out. I quit. Well, the problem for our purposes, there are now two problems. One, we've lost some statistical power because our sample size shrank. But the even bigger problem is that if students who have very low GPAs drop out and we don't observe them, that could actually cause an upward bias in the average GPA of the sample that we get. It's like we've chopped off the lower tail of the distribution of college GPA because those people just gave up and left college. Well, if that's the case and there's an upward bias in our average GPA of our sample, that's called selection bias. So how do we deal with that? How are we going to handle data that are missing not at random? Well, let me show you a way to deal with it. So if we tabulate graduate, recall that we had 208 students who didn't graduate, and we don't have information about their college GPA. So we know we're missing 208 students. The problem is we don't know why. We don't know if these students are missing completely at random or missing at random or missing not at random. So we don't know. So how are we going to find out? Well, a way to start looking at this is to model the probability of graduating. Again, we're going to use a Probit model for the the binary dependent variable graduate. And we're going to include covariates we're going to include observed factors as well as unobserved factors in this model. Now, here's what's kind of interesting. I'm going to fit my primary model here at the top. And if graduate equals 1, I'm going to fit the model that's described here at the top. If graduate equals 0, it's just missing. For the primary model, the people are just missing. Those observations are missing. But for graduate equals 1 or 0, we're still going to fit this model, and I'm going to include roommate as that special variable again. Recall that I need a variable that's associated with the dependent variable in the auxiliary model, but is not associated with the unobserved confounder. And so here I'm going to use roommate, and here's the argument. Perhaps your roommate is also a student who's in your major, and the two of you sleep at regular hours, you study together, not a lot of distractions from your roommate, and so that might influence your probability of graduating. But maybe your roommate is your spouse and your 3 kids and your 2 dogs and the aunt that lives in the basement or whatever. Those are a lot of distractions, and so those sorts of distractions may lower your probability of graduating. And so that's the argument here for roommate being a student. But having a roommate who is or is not a student should have nothing to do with your ability. And so we're going to use roommate again as this special variable. By the way, this has a name. Economists call it an instrumental variable. I've kind of dodged that jargon, but if you're familiar with it, that's just an instrumental variable is all it is. Now, this is why I like using the structural equation model, because this allows me to really emphasize this point. I have the same model I had before here at the top, and I've added in probability of graduating here at the bottom. So I believe that having a roommate who's also a student, influences your probability of graduating. But notice that there's no solid arrow pointed directly back at college GPA. So I don't believe there's any direct influence of graduation on GPA. All I'm going to do is fit the model and allow the errors to be correlated with the primary model, where GPA is the dependent variable. Okay. Let me say that one more time. So I have these two models, the primary model where GPA is the dependent variable, and I have an auxiliary model, probit model for graduation. And I'm going to allow the errors to be correlated, but graduation does not go back in the primary model. So that's different than what we did with treatment, non-random treatment. So if I look at my eregress command now, it's the same eregress command where GPA is the dependent variable. I still have my other two auxiliary models, and I'm going to add a third auxiliary model here using the select option. So the select option, what that does is it allows me to fit another auxiliary model where graduate is the dependent variable, income and roommate, sorry about that, that's my phone. It's going to allow me to fit an auxiliary model where graduate is the dependent variable and income and roommate are predictors of graduation status. But the big difference in using the select command, first off, select is going to again fit a probit model because graduate is a binary variable. But the big difference with select is that it is not going to put graduate back in the primary model. So when you look at the output, graduate will not be part of the primary model. Okay. So I have a primary model, 3 auxiliary models, and when I look at my output, now it's getting more difficult to read because it's so small, but I have 4 collections of coefficients. Again, at the top, I have my primary model. This is the thing I'm really interested in, where GPA is the dependent variable. And I have an intercept, I have program participation, high school GPA, and income. So that's the model that I'm really interested in. And then I have my 3 auxiliary models here below. Recall that graduate and program participation, those are both probit models. So these coefficients are on a probit scale. And then I still have my auxiliary model where high school GPA is the dependent variable. Again, let's zoom in on the bottom part here because it's become so small, it's really hard to read. So this is just the bottom part of the output. Again, I don't see the variance of the error terms for the graduate model either because it's a probit model. And again, the variance of the error terms is constrained to be 1. But what I do see here at the top of the correlations is the correlation between the error term for the graduation model and the error term for the GPA model. And that correlation is 0.76. The p-value is 0.000. So this suggests we definitely have this issue of endogeneity, or more specifically, non-random treatment, data that are missing not at random. And so the good news is, again, by fitting the model in this fashion, using the eregress command and that select option, we should have corrected for any selection bias. By the way, just in case you're wondering, because this still baffles me to this day, the details of this, why does this work? It's nothing new, actually. This is just Heckman selection. So if you're familiar with Heckman selection, essentially that's all we've done is we've fit a Heckman selection model here. And we do that by using the select option. So select here is it's identical to using the Heckman selection technique. Okay.
Could this be the reason that the model that you showed last has 1,000 observations rather than 792?
Yes. Thank you. Excellent point. So if you notice the number of observations, and you'll see that in the table as well here in a moment, this model actually includes 1,000 observations rather than just the 792. And it even breaks it down for you at the top of the output, where it says selected 792, non-selected 208. And in fact, if we look at this table here, so this is that, remember I've been typing estimate store along the way. If I type estimates table and type the names of all the models I've fit, notice the last column here, I've called it end cell for endogenous selection. And it now includes coefficients for all of the variables that we included in our model. And note that it does have 1,000 observations in the model because it includes the selection component of the model. So what have we done here? What's the punchline of all of this? Well, recall that I mentioned that these are simulated data. So I actually know the true parameter values that I use to simulate the data. And so here at the bottom, I can look at the true model parameters. So I'm not going to go through the entire table. I'll leave that to you to just glance around. But if you just look at the last column here, the intercept was minus 0.6. The true parameter for the intercept was 0.6. If I look at this table, the column at the far right, the model N cell that takes all of these features into account, that parameter estimate is 0.6072. So it's spot on 0.6. The true coefficient for the treatment effect of the effect of the treatment is 0.3. If I look at my output here, notice that it's 0.2977. Even for the N-treat model, where I took the endogenous treatment into effect, it's 0.3044. So that effect, the program effect, is now unbiased or consistent. And then the true parameter for high school GPA is 0.9. And if I scan across here, once I start taking that endogeneity into account, I get 0.9, 0.9, 0.8936, which is essentially 0.9. And then lastly, income, the true parameter is 0.8. And the only one that comes even close is this final model N cell, which is 0.8221, which is pretty close to 0.8. Now, this was not a simulation study. I didn't run this 1,000 times and take the average parameter. This is just one data set. And so this is not meant to sort of defend or prove the idea that this is unbiased. But what it is showing is that if your data set does have these features, having a model that will allow you to model those features correctly or correctly specify your model will get you back parameter estimates that are very close to your true parameter estimates. Okay. So those are the three features of common features of observational data that we might encounter and how we can deal with them using the eRegress command. So let me talk quickly about post-estimation. Stata has an estimation post-estimation paradigm. So you fit the model using a command like eRegress, and then after you fit the model, you can do things like use the predict command or the margins command and margins plot. After you fit an eRegress command, there's also a post-estimation command called eStatTeffects. And what this allows me to do, after I use eRegress, I can type eStatTeffects, and this will estimate the average treatment effect for the treatment variable. And Stata knows that program is the treatment variable because we used the N-treat option right here. Recall that I mentioned that if you use N-treat, Stata knows that's the treatment variable. Well, that's how I can just type eStatTeffects and Stata automatically knows that program is the treatment effect. Now, in this example, we didn't have any interactions with program. It was a very, very simple model. And so when you type eStatTeffects, you essentially get back the parameter estimate from the model. But it's not always going to be that simple. And so if you had interactions of program with other things like age, or you might want to include an interaction between program participation and high school GPA, for example. And so if you start building more complex models, eStatTeffects will tease all that stuff apart and calculate the marginal treatment effect for you. You can also use the ATET option. So if you type eStatTeffects, ATET, that stands for average treatment effect among the treated. And what this is estimating is it's answering the question, what would the effect have been had the people who were treated not been treated? What would the difference be? So this is the average treatment effect if you were to just consider the folks who were treated. Now, again, it's equivalent to the parameter estimate here, but that's because we used a trivially simple model just to make it easy to understand. You can also use the margins command after eRegress, but keep in mind, you really want to read the manual if you're going to do this. We actually had to add some machinery to margins to allow it to work after eRegress. And so you'll notice some things in here like predict, fix. So you may need to fix some things in here. So I don't have time to go into the details in this talk, but if you're going to use margins after eRegress, I strongly recommend reading the manual so you understand what this predict fix part of this means. But that allows me to then use margins plot, and I can actually plot the results of my models. Now, I've only shown you eRegress for continuous outcomes, but there are actually commands called for eIntReg that will handle interval outcomes, eProbit, so if you have binary outcomes, and eOprobit if you have ordinal outcomes. So Stata can handle all 4 of those different variations. The biggest request we got after Stata 15 was, hey, I'd like to do this with panel data. Is there a panel data version? So in Stata 16, we added panel data versions of all of these. So there's now an XT-eRegress command, XT-eIntReg, XT-eProbit, and XT-eOprobit. So you can fit panel data extended regression models, all the same features you saw here, but allowing for panel data. Now, I've kept this model as simple as I possibly could to make it sort of easy to digest in an hour. But you can do much more sophisticated things with eRegress than I've shown you here. You can include polynomials of endogenous covariates. You can have interactions of endogenous covariates. You can have interactions of endogenous covariates with exogenous covariates. So you can fit very sophisticated, much more realistic models. I've just kept it simple here so that it's not too confusing. Now, causality, let's talk about that for a moment because we haven't really talked about it. And I include this as a cautionary note. There's nothing in the eRegress suite of commands that magically extracts causal relationships. Okay, it's not the math, it's not the command that does this. I've actually heard people say, oh, well, I was doing regress, but I wanted to do something causal, so I used structural equation modeling or I used extended regression. It's not the math and it's not the software that makes it causal. Any kind of statistical model you fit depends on the underlying scientific rationale. You have to have a scientific rationale for the causal inference, the causal effect, or the causal relationship. And the other thing you need is a correctly specified model. And that's where the eRegress commands come in. They allow you to fit a correctly specified model. So if I just use the regress command, that does not account for the endogeneity, potential endogeneity in the data set. Or in the model. It doesn't account for the non-random treatment assignment. It doesn't account for the data that are missing not at random. And so that's where eRegress comes in, is it allows you to fit a correctly specified model that gives you consistent or unbiased parameter estimates. But you still need some sort of reasonable underlying scientific rationale for the causal nature of the relationship. Okay. So that's it. If you have any questions, shoot me an email anytime. I'm better about email lately because I'm not traveling. Normally, I spend about half my time traveling to universities, but COVID has put a stop to that for a while. And again, you can download the slides from this tiny URL here at the bottom, tinyurl.com/2019 causal inference. So thanks again for coming, and I'll be happy to hang around and answer any questions for as long as you like. I don't have to be anywhere today.
Thanks, Chuck. Thank you
Sure.
very much. Really, really helpful. It's very important for people to know that there's life after regress. So
yeah.
Yes. So we would like to keep it open. So for those participants who either want to ask a question, either through the chat box, you can type it up, or you can unmute yourself and ask a question.
This might be a stupid question, but what is the what's the definition of all the, you had in a whole bunch of places a variable not equal to 0? Just like, what does that actually mean?
Correlation, rho.
Oh, right. The correlation is not equal to 0. That's
Gotcha.
not a dumb question at all. And I have lots of dumb answers too. So, but yeah, that's what the rho is. Rho is the correlation estimated correlation between the error terms. And so if that correlation is 0, what that suggests is that you don't have any problem with endogeneity, and you can go back and use the regress command and be confident in your results.
Gotcha. Thank you.
Sure. Any other questions?
Can I ask one?
Sure.
Can you use an example to like ideally a simulated data set to demonstrate the advantages of eREG, IVREG, and ETREG? Is there, I mean,
Oh, I see what you're saying. From the treatment effects versus the
yeah, because you've
e-regress
got a
family.
bit of a treatment model here too, right? And that the program is a treatment.
Yes. Excellent,
Very
excellent question.
There's a follow-up to this. I took a course with David Drucker
Yes.
on treatment effects, and there's an excellent manual on treatment effects. And I don't know how related this question is, but often the examples or simulated data, they do not show something above and beyond the regress model. So you see the coefficients coming out of regress models are almost the same as coming out of treatment effects and whatnot. So how do we illustrate that the all this extra effort of taking care of endogeneity and selection bias and whatnot,
right,
real data sets can really demonstrate the true impact?
Yeah, this is an excellent question. And if I start to ramble, somebody please shut off my microphone. So clearly you're very familiar with Stata's causal inference tools. So there is another collection of commands or suite of commands that's the treatment effects commands. They do things like inverse probability weighting and the doubly robust estimators and propensity score matching and those things. Those came out back in Stata 13. And it's funny you mentioned the manual. I actually wrote the original manual back in Stata 13 for the treatment effects features. And it was great fun because at the time I didn't know that much about it. And so as a lot of things that I do, I had to learn along the way and then explain it to other people. And essentially what that collection of commands does is it's looking at, it's targeting the problem of non-random treatment assignment. So remember, we had 3 issues that we were talking about with observational data. The treatment effects suite, things like propensity score matching and inverse probability weighting, those all tackle the problem of non-random treatment assignment. That's their purpose. Now, I believe in Stata 14, we added some ability to handle both endogenous covariates in the context of models that had non-random treatment assignment. And so that was sort of the beginnings of what you now see with eRegress. In Stata 13, it started off as the treatment effects issue. We also had separate commands. Someone brought up IV regress. So we had the TFX commands do non-random treatment assignment. IVReg deals with instrumental endogeneity. And then we also had the Heckman command that does Heckman selection. What eRegress brings to the party is it brings all 3 of those features together. And so it allows you to deal with all 3 of these issues in one command rather than using TFX like propensity score, IPW. That deals with the non-random treatment part. There are some variations of those commands that allow endogeneity. So that tackles 2 of the problems, endogeneity and non-random treatment assignment. The thing that eRegress brings over and above that is the ability to also deal with selection issues, missing data that are missing, not at random. And so in a sense, if you don't have problems with selection, you could go use the TFX suite of commands, and there are E versions of those. There's so many, I can't remember what they're all called, but there's something like I don't remember the exact command, but if you look under the treatment effects part of the statistics menu in Stata, it has all the treatment effects commands, and then it has the treatment effects commands that allow you to deal with endogeneity. And so in that sense, if you didn't have problems with selection, then you could use either command. You could either use eRegress or you could use the treatment effects with endogeneity. But primarily the treatment effects commands were designed to just handle the problem of non-random treatment assignment, which is one of the 3 issues we dealt with here today. Does that answer your question, or?
Yeah, yeah.
You want to restate
Yeah.
it? Okay, great.
Yeah, because I've for many years we've been using IVREG as a 2-stage least square model to handle the endogeneity problem.
Yes.
And a separate stream, just like you described, the treatment effect is another set of thing. And then I've seen the example that at the beginning you said this is a simulated data, quite normally distributed.
Yes. Yes.
It's quite interesting to to see whether, let's say one day we have a bit of data collected, and then we're trying to see which model or which sets of model that we wanted to use first.
Right.
Leave out the Heckman's model first. Let's say we have a bit of an endogeneity problem here. Could be
Right.
caused by omitted variable problem, or other type of causes for endogeneity.
Right.
What would you recommend to start first here?
Between the two commands,
Yeah.
well, first off, keep in mind, I'm a biostatistician, not an econometrician. So I'm guessing that every one of you knows more econometrics than I do. I'm the dummy in the class.
Oh,
Take what I'm going to say with a heavy dose of salt, because again, you guys know a lot more about endogeneity than I do. I would probably maybe start with IV-Reg, to be honest, because there are things that you can get out of IV-Reg that you cannot do with eRegress.
Okay.
So there's, what is it, the inverse Mills ratio or something like
Yeah.
that. Other diagnostic tools and things that are available with IV-Regress, if that's the only problem you need to deal with is endogeneity. And I believe there may be things about, certainly with treatment effects. Let me back up and talk about treatment effects again for a moment.
Sure.
So what eRegress is doing, the eRegress command that I just showed you, it's using a technique called regression adjustment. And so if you're familiar with the TFX suite of commands in Stata, there are 6 of those estimators. There's regression adjustment. Let me see if I can get them all off the top of my head. Regression adjustment, inverse probability weighting, IPWRA, which is the doubly robust estimator. And then there's the augmented IPW. And then there's nearest neighbor weighting and propensity score, nearest neighbor matching and propensity score matching. So you have 6 choices. I bumped my microphone. So with the TFX suite of commands, you have 6 different kinds of models that you can use for dealing with non-random treatment assignment. With eRegress, you only get 1. With eRegress, you have regression adjustment. So you can't do IPW, you can't do propensity score matching. Now, the good news is if you play around with those other 6 estimators, you typically get pretty similar results. So whether you use nearest neighbor matching or you use IPW weighting, the results are pretty close. So it's not that big of a deal. So if you were only dealing with non-random treatment assignment, I would absolutely go check out the treatment effects, TFX suite of commands, because you have a lot more choices and a lot more features. But what eRegress allows you to do is if you have all 3 of these issues or any pairwise combination of these issues of endogeneity, non-random treatment assignment, and data that are missing not at random, if you have all 3 of those problems, eRegress is it. It's really your only option. But if you have any of those problems individually, I would probably go back and use the other ones just because they have more features. Does that answer your questions?
Thank you. Indeed.
Thank you. Yep.
So we have the mic open.
Yes.
Excuse me, can I ask a question?
Sure.
Yes, go ahead, Ali Raza.
Yeah. Thank you for your great presentation. It was actually very helpful. My question is, I'm actually working on transportation, and I usually use generalized linear modeling. So I was wondering if the e-regression can be used for other modeling types like GLM or especially GLM.
So the short answer is no. The slightly longer answer is yes, sort of. So you have to have an error term. So you notice that we use probit models for the like, even if you want to fit a primary model that has a binary variable, you have to use probit. And the reason is because logistic regression doesn't actually have an observation level error term. And you have to have the error terms to deal with the correlation and all of that.
Yeah.
So there were 4 different flavors. There's the continuous. So you can have continuous dependent variables. You can have binary dependent variables, interval variables, interval outcomes, or you can have ordinal outcomes and use ordinal probit models. So those are sort of your choices: continuous, interval, binary, or ordinal. There will never be a logit. We normally don't talk about things that may or may not come out in Stata. But that's one I can categorically say, because it's mathematically impossible to do a logistic version of this. Whether there's Poisson, I don't know. I talked to Charles a long time ago about this, that Poisson is very difficult for mathematical reasons. So I don't know if when that would ever appear as part of this. So but if we had Poisson, that would sort of tie up most of the common outcome types. But for now, you can fit models with continuous outcomes, binary outcomes, ordinal outcomes, and interval outcomes.
Great, thank you.
Sure.
The transportation colleagues use a lot of discrete choice, McFadden's logit model. So that's probably not part of ERM right now.
Right. But you might could fit it if you, depending on how you want to interpret the results, you could fit it if you have binary outcomes using eProbit.
Yes.
Yeah.
And even though the coefficients you get out are strange and you don't get odds ratios, you could use the margins command to calculate predicted probabilities at certain values of covariates. So that could work.
Yeah, marginal effects, yeah.
Yeah.
And there's a multivariate probit model, but not part of eRegress, right? The ordinal is, but not the multivariate probit.
I don't think you can do multivariate with eRegress, but you can do all kinds of multivariate things with the GSIM command. So I don't know if you're familiar with Stata's GSIM command.
Yes.
But that allows you to have multiple equations, simultaneous equation models. Now, the one that I don't even pretend to understand, I vaguely kind of know what it is generalized method of moments, or the GMM command.
Yes, that's Sophia Rabe Haskett's command, GLLAMM. The generalized linear, latent, and multimodal models, right?
Yes, that's an older user-written command, and it's really cool as well. But there's an official command called GMM, which stands for generalized
methods of moments. Yes.
Right. And so that allows you to deal with endogeneity with simultaneous equation models. And that's about all I know about GMM. That's we've reached the end of my knowledge of GMM in about 2 seconds. But I know economists love it. It's a major tool in the economist toolbox is GMM.
Absolutely.
Yeah. So let me read some of the questions in the comments box. I don't know if these people are still in the room or not. One of the questions says, do we need to manually draw those paths, or the system will auto-generate based on the data? The short answer is no. The Stata will not automatically draw the diagram for you. You draw the diagram. It goes the other way. You draw the diagram, and then you can hit estimate, and Stata will take the diagram and generate the command for you. But it won't go the other way. You can't just type a command and have it create the diagram for you. But a lot of people really prefer to draw their path diagrams and then use that to generate the command, and Stata will do that. Here's one that says, what happens if you omit an important variable for y, but that omitted variable isn't correlated with the other included covariates? Let me read it again. So like, what happens if you omit an important variable for y, but that omitted variable isn't then you would have no problem. So that's an excellent question. What happens if you have an omitted variable, but that omitted variable isn't correlated with any of the other covariates in the model? Well, then you don't have a problem with endogeneity, because remember that the correlation is induced by omitting a variable that was correlated with another covariate, in which case you could just ignore it. You don't really have a problem. Does that make sense?
You can ignore it, but it will influence the parameters of coefficients estimated for other parameters.
Oh, yes. Well, that's true. Yes. But
it will inflate or deflate some of the results of other variables.
Right. But you won't have that traditional endogeneity.
Yeah, the endogeneity is gone. Yeah.
Yeah.
But everything is correlated with every other thing. So
generally a true statement. Okay, in Stata for sim models, can one either write the code or draw the diagrams, a relevant variable not included in the model results? Yeah. So yes, you can, as I mentioned earlier, you can draw the sim diagram. You can draw it and then press estimate. There's a little button, and it will take the diagram and create the code for you. And it will even show the parameter estimates on the diagram if you want. Let's see. If the omitted variable is only a determinant of y, not correlated with x, we have a larger error term. Technically, the larger part of the variation. Yeah, that's more of a statement than a question, I think.
Yeah.
How do you identify the unobserved confounder? Ooh, that's a good question. And I will just give the sort of corny answer that you would have to fit one of these models and check to see if there's correlation between the error terms. And I think with that, I'll punt to Professor Hayter for maybe a better explanation. Do you have a better? So the question is, how do you identify the unobserved confounder?
I think probably going with the theory first, right? Like you have to have a theoretical foundation for making such assumptions and then testing them, right? So
Right.
basically, any sort of relationship, either confounding or indigeneity, or the absence of it, is a assumed position we take. We have a hypothesis, and these tools are very capable of then testing, allowing us to test our hypothesis one way or the other, right? But we start with a theoretical basis for what we're going to test.
Excellent point. Yeah. Oh, somebody already answered that actually. Okay, here's one that says, in that case, why not we include the variable in the main model? That is, the variable has no data in the data set. I'm not sure I understand the question. In that case, why would we not include the variable in the main model? Is that the variable has no data in the data set? I'm not sure I understand the question. So Sajjad Hussain,
what they're trying to say is that the only reason you're not including a required variable is perhaps because you don't have it.
Oh, right. Sure. Yeah.
I'm guessing that's the intent of the question.
Okay. Yeah, that's one of the things about observational data is that unlike an experiment where you carefully choose all the data in the data set, these are like data that you're just walking along and find it on the sidewalk and you're stuck with what you find, right? You didn't get to necessarily choose all the variables. Sometimes you could, I suppose, but sometimes you just have whatever is in the data set.
Someone who's sort of cynical about this once said that the good papers on instrumental variable regression is where people first found a good instrumental variable and then found a problem for it. Because if you have a problem, then finding an instrumental variable for it is quite difficult.
Yeah.
So always look for a variable first and then see what problem can be solved with it.
Find the answer first and then ask the question. So.
Yes.
Good strategy.
Great.
Other questions?
Folks, we have time for 2 more questions, so please be bold, unmute and ask. We have still 32 people online with us.
Can I ask a question?
Please go ahead.
Absolutely.
It was actually me who was answering the questions in the chat, so I'm really sorry for that if that wasn't, wasn't the right thing to do. And the other thing is the example we considered in the non-random assignment problem. There was something that we called the endogenous treatment at play. So does the e-regress also cover when we talk about the exogenous treatment types?
Yes. So we used the N-treat option. There's actually an X-treat, or is it X-treat or just treat? Somebody will have to double check me on that. But when you specify N-treat, Stata treats like program participation, it treats it as an endogenous treatment. But a treatment could be exogenous. And eRegress will deal with that as well. So the option becomes either just treat or X-treat. I can't remember. But if it's endogenous treatment, you do have to specify N-treat. So it will handle either one, exogenous treatment or endogenous treatment.
Basically,
did I understand the question?
Change the syntax and we can include the exogenous treatment in there.
Yes. Tell you what, let me open Stata really quickly and see. Often when I run Stata and I'm broadcasting at the same time, it gets really, it bogs everything down, but so eRegress, endogenous, oh, it is X-treat. So the option is X-treat. So if you have exogenous treatment, you would type X-treat as the option. And if you have endogenous treatment, it would be N-treat.
Chuck, can we give an example where when we will use an N-treat and when we will use X-treat so that students can have an idea?
Off the top of my head, let me think for a second. So in this case, program participation was endogenous. And the reason it was endogenous is because we believed it was related to a student's ability, right? So we had this unobserved confounder ability. And so we thought that, well, maybe people of higher ability are less likely to take the treatment, the program, I'm blanking on the term, and I just said it. I just did a whole talk about it. The study skills program. So people of higher ability are less likely to take the study skills program because they think, well, I did well in high school. I'm generally pretty good test taker, so I'm not going to take the thing. But if there was no reason to believe that program participation was associated with something like ability, then you could just say it's exogenous. The only reason we've treated it as an endogenous treatment is because we believe that program participation is correlated with ability.
So may I suggest that if we look at the students' IDs and those with even last two numbers making an even number could be treated, and we say, well, those with the odd last two numbers, like if your last two digits are 13, you are in the program. If it's 22, you're not in the program. So that would be probably a treatment decision made at random, but still not endogenous with the ability or anything else.
Well, it would be sort of random if you use some sort of an ID. Well, is it really random? I don't know. But yeah, that's a good example.
Because the ID that you get allotted when you join a university has no bearing on your high school GPA or whatnot.
It should be fairly random.
The odds of getting an even last two digits or odd last two digits could be assumed to be random.
Yeah.
Can I say something?
Absolutely. Please.
What Professor Heather just pointed out is something like a systematic random sampling, where we have a specific set of last digits for student IDs where we're going for the treatment.
Yes. Someone asked me a question a while back, and I was stunned to find out you could do this. I'm pretty sure that you can incorporate survey weights into this as well. I already closed Stata, but that came up, and my guess was the answer was no. Hang on just a second. Help. Options. No, I may be wrong about that. It may have been something else. No, I don't think you can incorporate survey weights.
For Stata 17 then.
No, although it would be funny. I wouldn't be the first person to give something away in Stata. Funny story. Are we still recording?
Okay, hold on.
Oh.
Still recording. Let me just stop recording because
okay.
Can't actually stop recording. So just give me a second. Do you want to stop?
Sure.
Okay, and just give me 1 second. I have to stop the live.